squared plus 2x plus 2. And when I set this equal to 0, because I know I will not have we will not find critical numbers coming from f prime being undefined. That's correct, right? That's clear because it's a polynomial function. Then I divide by 2. 3x squared plus x plus 1 equals 0. X equals negative b plus or minus b squared minus 4ac over 2a. Not real. No critical numbers. Thank you. Next question. 2 times a. Anything else? Other questions? Anything else that you came across? Anything you'd like to review? So our test 3 is on Tuesday, correct?
Test 3 is on Tuesday,
And the
checklist in Tuesday.
On Tuesday.
Okay.
Yes.
The test quiz.
Yes. You can put them over the desk. Thank you so much. Anything else that we came across? Anything else that... Which one?
Newton's method.
Yes. Yes. Let's choose a problem with Newton's method. Or we can make one up. As long as it doesn't have a solution at negative 1,500, 1,000, billions. Because we have to find an interval, right? That's okay. You still have time.
We probably wouldn't use a radical problem.
Okay, so let's look at Newton's method at the end of 4.8. I don't know, what about 25? 25 caught my eye. And let me know if this is something you would like to work with. I have no idea where this is going.
Looks exciting.
So we're asked to solve or find all solutions. Just remember, I only want one. Because I know that if you know how to find one, you will know how to find any. So x over x squared plus 1 minus the square root of 1 minus x is 0. This is the function we are working with. We have to find its derivative. Ugly, but don't try to simplify, there is no need. Top prime is 1 times the denominator minus the top times the denominator prime over x squared plus 1 squared minus 1 over 2 the square root of 1 minus x times negative 1. Let's take a moment and see if this is okay. Is this okay so far? Okay. Then I will try to simplify a little bit. I will not do anything here, but I will change this into positive. And I will simplify just a little bit, but not combine like terms. I mean not find the least common denominator and then combine like terms. No, I will not do that. So f prime of x equals 1 minus, this is 2x squared plus 1, right? So 1 minus x squared over x squared plus 1 squared and plus 1 over 2 the square root of 1 minus x. Is that okay? So the function that we want to create in order to put in the graphing calculator will be, can anyone dictate?
X.
Minus the function at the top and the the derivative in the denominator. Now I will put the function in the graphing calculator. Ready? So the x equals, and y equals, we have the function first because we need to find the interval. So x over, in parentheses, please, x squared plus 1, close the parenthesis, minus the square root of 1 minus x, close the parenthesis.
I forgot x to the end. It's like x minus.
This is just a function for now.
Gotcha.
And then I'll put the, because we don't have the interval yet. So then let me check whether, okay. Second and table. Obviously the function, the domain, let's discuss that because that's very important. So I see that this portion exists everywhere. But this one requires 1 minus x to be greater than or equal to 0. Or x less than or equal to 1. So I have to look for a solution to the left-hand side of 1. Just making sure where we start. Okay. So I'm going to plug in -4, see what happens. Then -3, see what happens. -2, -1, 0. Can I plug in 1? Yes, I can plug in 1. That's it. I found a solution somewhere between 0 and 1. So the interval is 0, 1. However, I have to be very careful. Look at the derivative. Can I start at 1? No. I cannot start at 1. Because I will not go past any step, right? Not even the first step. So then I will say I start with x0 equals 0. Now I go back to the calculator and put in g. So careful, do not delete what you have. Just insert, second and insert, and put x, and then minus. Put parentheses for the top, parentheses at the very end, and divide by, in parentheses, now I put in the derivative. The top, 1 minus x squared, close the parenthesis, divided by, in parentheses, 1 plus x squared, or x squared plus 1 squared, plus 1 divided by, in parentheses, be very careful now. I said plus, but I wrote minus. Nice. Very careful. You either write 1 divided by 2 and then further divided by the square root, or you put parentheses as 2 the square root of x minus 1, go outside, put another parenthesis, and another parenthesis for the denominator. And now, second and quit, we go to variables, function, I call function y1, and I will plug in 0. Let's see what I did. X minus x over x squared plus 1, correct. Minus square root of 1 minus x, yes. Parenthesis outside, yes. Left, yes. Right, yes. Okay, that's the denominator, what I did. Parentheses, 1 minus x squared, yes. Divided by x squared plus 1 squared, yes. Plus, yes. 1 divided by 2 square root. Ah, got it. 1 minus x, of course. 1 minus x, parenthesis, and parenthesis. Of course, makes sense. And parentheses for the inside, parentheses for the outside, another one. Okay. Another shot. It cannot be an error now. Okay. So 0.66666666. If we want 6 decimal digits, I will copy 7. So that's my what? What is this? X1, right? The first iteration. So 0.6666666. Okay. Then second an entry, and I overwrite with the previous answer and close the parenthesis. What is this? X2. 0.768947. 0. And from this moment on, I just repeat. Nick, is this okay?
Yeah.
Okay, this is X3. 0.7668282. And I have now 1, 2, 3, 4, 5. So I'm assuming just one more. 7668257. And the next one should be identical with this. The first 6 digits. Yes. So you don't need the last one. So the method converged in 4 iterations after the initial value. Is that okay? Okay. Anything else? Other questions that you would like to go back to? Anything else? Anything else?
Can we do
Yes.
the 42 on page 298?
42 on 298.
Or 299?
42. Yes. What was the problem with this?
Is this the one where you put the y equals?
No. This is, you mean to differentiate?
You do. So you
I don't need to,
differentiate the-
because I have a differentiation rule for natural log of a function.
Okay. I start thinking about the y equals and then.
No, so let's summarize when we do that.
Mhm.
In 2 situations. When we want to differentiate, Thank you, sorry, thank you, sorry. When we, for example, want to differentiate 2x plus 1 raised to 1 over x, we don't have a formula for this. No differentiation rule. Since there is no differentiation rule, I have to denote this by y, apply log, and differentiate implicitly. Here's a second situation in which I have no choice, is when I'm asked to find the limit of this. 2x plus 1 to 1 over x, when x approaches infinity, for example. I have no choice. Must use natural log. In no other case is mandatory. Using log is mandatory. No other case. You could in certain situations. What kind of situation? For example, I don't recommend it. But when could I use natural log? Yes, indeed. With powers. Especially ratios with powers. Like, for example, x squared plus 1 to the 4th power over x minus 3 to the 5th power. Because if I apply natural log to this, then I will have 4 natural log x squared plus 1 minus 5 natural log of x minus 3. And yes, indeed, it will be slightly easier to differentiate. But then if I want to change it into a fraction, I will still get to the same thing, meaning I have to find the least common denominator, I have to multiply, and so on and so forth. So here I can. It's not forced, I'm not forced to, but here I have no choice. These are the only two situations in which I have no choice. I have to use log. I denote the function by y, I apply log, and then I either differentiate implicitly or find the limit. First I find the limit of the natural log, and then I swap the operators. But this function should, I think, let me know, it should not give any difficulties. You will be able to easily find the domain, the derivative, the second derivative, and come up with a table with no problems. The limits will be easy. Now let me know. I'm sorry?
Are we doing that one?
This one?
Yes.
Only if it's necessary. This is all from the checklist.
Okay. Can we do it?
Yes, I'm going to do a different one similar to this.
Okay.
So it may not work that beautifully because it's only because if I do it, I have to do it for everyone.
Okay.
That's my point.
Well, I guess it's similar.
Right, but this one is probably, I don't know, I have not even looked at it, to tell you the truth. I haven't done it. But what I was going to say is this may work well and get easy to simplify in the long run for the first derivative because they probably use the computer algebra system to come up with a function. Who knows down the road? But so the problem is how to differentiate it, or what do you think could be the problem? How to differentiate it would be the
I
problem?
think after differentiating it and filling out the table.
That was the difficult part? Okay, let's do it together then. So we have f of x equals natural log of x to the 4th plus 27. First I have to find the domain. What is the domain of this function?
The open at 0.
On the inside, so that's where the 4th root of x equals.
Okay, so let's talk about this. Any log in any base has to be applied to what type of number? Only positive, not 0, right? Only positive. Good. So let's look at x to the 4th plus 27.
Negative.
It will never be negative. Will it be 0?
No.
No. So then the function is defined everywhere. So we get the chart or the table going. Very good. So negative infinity to infinity, 0 has to be in the table. When x is 0, how much is f of 0? Log of 27, and I have no idea what that is. So natural log of 27 is 3.3. Here he is. We were just talking about you. If you want to shut the door, that's great. Good. Now let's find the limits. The limit of natural log when x approaches infinity. Very good. The limit of natural log when x approaches negative infinity. That's it. Because negative infinity to the fourth power is still infinity, and natural log of infinity is still infinity. Are you okay so far? Ready for the first derivative? Okay. So f prime is 1 over x to the fourth plus 27 multiplied by 4x cubed. Is that okay? Jason, we are working on a problem from the checklist, 42 on page 299. Okay, so then this is 4x cubed over x to the fourth plus 27. I need to set it equal to 0. When I set it equal to 0, I get only one solution, which is
0.
very good. For the purpose of studying the sign of this expression, I will break it up like this. Because I don't want to waste my time with this quantity. What sign does this quantity have that I don't want to waste my time with? Always positive. Always separated, because you need to find the sign of the derivative. So why would you bother to square, multiply, divide, and so on and so forth if this piece is always positive? So to the left-hand side of 0, what is the sign? To the right-hand side of 0, what is the sign of the first derivative? Perfect. So I already know that 0 comma 3.3 is very good. Let's see if these two work well together, from infinity to 3.3 and from 3.3 to infinity. Is that okay? So far, so good? Now I will differentiate this function. I refuse to take that and carry that forward, just to increase my numbers everywhere. 4 is a constant. It's a factor constant. It's not plus. If I had x cubed plus 4, I could have not done this. But this is a factor. It can stay outside. Is that okay, everyone? Okay. So I'm going to differentiate to get the second derivative. 4, the top prime, 3x squared times the denominator, minus the top times the denominator prime. So far, so good? Looking to see if I normally carry, I don't know if you want, Bryce, I normally carry Ricola cough drops.
Okay.
Would you like?
If you have some, that'd be great.
They're so good. Yeah, I don't know. I don't know. Oh, I found one. I found three. Somebody else is talking here. Yes. Thank you. They always help me, but.
Yeah.
Okay. 4. Obviously, I will factor out an x squared. And then 3 x to the 4th plus 81 minus 4x to the 4th over x to the 4th plus 27 squared. So now I have 4x squared negative x to the 4th plus 81 over x to the 4th plus 27 squared. Factor out negative 1. And then this becomes x to the 4th minus 81. Which is factorable. Negative 4x squared. X squared minus 9 and x squared plus 9. X to the 4th plus 27 squared. And this is negative 4x squared, and this is x plus 3. X minus 3, x squared plus 9, x to the 4th plus 27 squared. All this prep is very necessary. You know why? Because we are going to set it equal to 0 and find points of inflection, right? So then the second derivative is 0. There are 3 possible solutions.
That's a 0.
0.
Oh, x is greater than I do.
Exactly. Negative 3, 0. Oh, I didn't mean to put it there, sorry. I did not determine that yet. Zero, 0, 3, 0. Now I studied the sign of the second derivative, and let's see what I don't need. Definitely this I don't need. I'm not going to even look at it. X squared plus 9 is positive, 4x squared is positive, x to the 4th plus 27 is always positive. So don't even look at those. I'm looking at negative in front, x plus 3 and x minus 3. So when I plug in negative 10, negative, 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 sign.
That's negative.
I plug in negative 1 now. Positive, negative, negative. Plug in 1. Positive, negative, negative. Positive, negative, negative. And I plug in 10. Positive, positive with negative in front.
Negative.
I need to find this number, and I need to find this number. And it's all done. And I have to identify whether the function is symmetric or not. So natural log of 81, right? 3 to the 4th. 81 plus 27. I got 4.7 approximately. So that's correct. Yes, yes, and yes. So then, negative 3 is 4.7. What is it?
Plus
Is 0, 0 an inflection point? I mean 0, 3.3. Is this an inflection point?
No.
Because
It's not
the second derivative doesn't change sign. What about 3 comma 4.7? Inflection point. Very good, awesome. And now symmetry. Remember, we have to determine f of negative x. If it equals f of x, the function is even. If it equals the opposite of f of x, the function is odd. It cannot happen that both cannot happen at the same time. There is one function that is symmetric with respect to the origin and with respect to the y-axis, but it's a function that nobody cares about. It's y equals 0. This is the only one that is odd and even at the same time, but who cares about it? Good. So obviously you agree, I'm sure, that if we replace x by negative x, nothing will happen. The function will stay the same. So then therefore the function is even. Meaning whatever I graph on the right-hand side of the y-axis, I have to graph on the left-hand side of the y-axis. Okay, ready? All I need now is the table. Everything else is not important anymore. Okay. I plot the points I have first. 0, 3.3. Negative 3, 4.7. And 3, 4.7. The function is coming from infinity, decreasing, opening down to the point negative 3, 4.7. At this point, it changes concavity, opening upward, and decreasing, continue to decrease to 0.0, 3.3. The rest I'm not interested. I know the function is even. I just have to copy. I couldn't care less about the rest of the table. It turns out that the function has an absolute minimum at 0, 3.3 approximately, and a local minimum. It has 2 inflection points. It's decreasing on the left-hand side of the y-axis, increasing on the right-hand side of y-axis. It has 2 inflection points, as I said, concavity opening upward between negative 3 and 3, and opening downward between negative infinity and negative 3 union 3 and infinity. Very good. Is this clear? Okay, and I promised some changes may occur, but I think that Bob Newton has that class, 192-400, Tuesday, Thursdays from 7 to 8. And it's in Math 204. So if you're interested, I tried to get this class, but he was assigned to it before I. Okay, so it was. I thought I saw it, so I brought it up for you. Okay, anything else you would like to go back to? Any other problem? Anything from checklist or not? Anything you'd like to work on? Any questions? So our test 3 is on Tuesday. It covers chapter 4, not 4.9, and you don't have to turn in the checklist from 4.9, not now. And it will be part of the next one. And not 4.6. We've been doing calculator work anyway, so I didn't make a special case out of 4.6. What else would you like to see? So in summary, you will have obviously a function to study on a closed interval in which you have to find max min, absolute max, absolute min. you have a function to graph, like for example this one. It wasn't that difficult, was it, overall? Okay. Yes, please. G.
4.9 and 4.6.
4.6 is just calculator work. And 4.9 we did not cover yet. I connected to chapter 5. It should have been in chapter 5, not in 4. Okay, what else? Newton's method problem, Rolle's theorem or intermediate value theorem, graphing a function given certain conditions, L'Hopital's rule.
Can we go back to distinguishing Rolle's theorem and the mean value theorem?
Yes. Let's go back to that. They are in section 4.2. Let's take a look. Let's say number 1 on page 288. F of x equals 5 minus 12x minus 3x squared. The interval is 1, 3. We're asked to apply Rolle's theorem and find the number C guaranteed by Rolle's theorem. At least one. So there are 3 hypotheses for Rolle's theorem and only 2 for the mean value theorem. So the 3 hypotheses are f continuous on 1, 3. That is true because polynomial functions are continuous everywhere. Agreed? Then I will say f differentiable on 1, 3, and we know that f is differentiable more than 1, 3. Differentiable everywhere. And now we have to check f of 1 and f of 3. If f of 1 and f of 3 are not equal, then we will say Rolle's theorem is not applicable here. So plug in 1. 5 minus 12 is negative 7. Negative 7 minus 3 is negative 10. Plug in 3. 5 minus 36 minus 3 times 9. It was 1, 3, correct? Yes. Oh, okay. Sorry. I copied the problem incorrectly. It's 5 minus 12x plus 3x squared. Okay, so one more time. 1 minus 12, negative 12. Negative 12 plus 3. So this is 8 minus, you know what I mean, negative 4. Okay, let's see what happens now with 3. 5, negative 36 is correct, and 27. So plus 27. So 27 is this correct? Is it 4? Is it negative 4? Okay, all 3 conditions are fulfilled. Therefore, Rolle's theorem is applicable. And I will say by Rolle's theorem, there exists a number C in the open interval 1, 3 such that,
F prime C equals 0.
very good. So I have to find f prime of x, which is negative 12 plus 6x. Then I write f prime of c, which is negative 12 plus 6c equals 0. Or 6c equals 12, or c equals 2. Is this a number in the interval 1, 3? Because if it isn't, then something is wrong.
Yes, it is.
It is. Because by Rolle's theorem, that's guaranteed if a function is continuous and differentiable and starts and ends at the same y value, it must have at least one term. Guaranteed. Now, the mean value, any questions on this problem? Any questions? Now, the mean value theorem, let's look at problem 9 on page 289. We have f of x equals 2x squared minus 3x plus 1 on the interval 0, 2. This time we only need two conditions. Mean value theorem is more relaxed than Rolle's theorem. So f is continuous on the closed interval 0, 2 as a polynomial function. And then f is differentiable on the open interval 0, 2 for the same reason. If these two conditions or hypotheses are fulfilled, then there must be a number c in the open interval 0, 2 such that
c equals
f of 2 minus f of 0 over 2 minus 0. Let's find f of 2, let's find f of 0. F of 0 is clearly 1, so f of 2, and of course this is by MVT. F of 2 is 8 minus 6 plus 1, which is 3. Let's find f prime of x, 4x minus 3. And now we write 4c minus 3 equals, this is this part, equals f of 2, which is 3, minus 1 over 2. 3 minus 1 is 2, 2 over 2 is 1. 4c equals 3 plus 1, 4c equals 4, c equals 1. And this better be between 0 and 2, since it's guaranteed by MVT. And it happens that there is only one such point. Okay, so L'Hopital's rule, optimization problems, Newton's method, graphing a function given certain conditions. Tom, is this okay for both? Yes? Okay, very good. Slant asymptotes, anything?
Can we do,
Yes?
60 on page 308?
60 on 308.
Or one like that.
I'm sorry?
Or one like that.
308. Let's 60 on 308, 307, 308, 60. Yeah, that's fine. Let's do it. Limit as x approaches infinity from x raised to natural log 2 divided by 1 plus natural log x. Am I correct? Am I seeing that correctly? Yeah, I think I am. Very good. This is a typical example with what?
infinity raised to 0.
Right, but it's a typical example in which I must use,
Natural law.
that's it. It's one of these two. Thank you. In which I have no choice. This one is really the most difficult type of problem we've seen, I think, in this chapter, right? I mean, even optimization problems can get hairy, and even graphing a function, showing everything can be, you know, cumbersome. But when it comes to something like this, we really have no choice. So in order to differentiate, I need to apply log. And in order to find the limit, I need to apply log to y. Okay? Good. So yes, let's start by seeing what it is. So the top is a number, and the denominator goes to? Good. So 1 over infinity is? Good. And this is infinity. This is a power. This is one of the most difficult ones to work with. It's an indeterminate case that is a power. I'm hoping to be able to change it into a product, and then the product is easy to change into a
Ratio.
That's it. So let's give it a shot. I'm going to denote this by y, x raised to natural log 2 over 1 plus natural log x. My next step must be, yes, natural log y on the left equals natural log 2 over 1 plus natural log x times natural log x on the right. Okay, this is a constant. I don't ever want to mess with that. So I'm going to rearrange it. It's a constant and it's a factor. If I had natural log plus natural log 2, natural log x plus natural log 2, I could have not done this. But this is a factor. Leave it out. Don't even look at it. It can even come out of the limit, right? Because we know one limit law. Limit of a constant times a function is the constant times limit of the function. So when I apply the limit to both sides, this I can go in front of the limit. I don't want to mess with it. It's just in the way. Okay, next. So in step 1, I denoted the function by y. In step 2, I apply natural log. In step 3, I'm not differentiating, it's a limit. I'm asked to find a limit. So what is the step 3?
The limit.
Apply the limit. Awesome. Thank you, James. So limit of the natural log y, which when x approaches infinity, is natural log 2 times the limit as x approaches infinity from natural log x plus 1 divided by 1 plus natural log x. I check again. What are you hoping for? We're hoping that the power change directly into a ratio. I don't even need to apply any algebraic manipulation to change it from a product to a ratio. So what about the top? What about the bottom? Nice. So this is natural log 2 times limit as x approaches infinity. The top is,
Whatever x.
the bottom is,
Whatever x.
the limit is,
0 to 0.
uh, 1 times.
That's a lot.
So then I copy the beginning. What beginning? Right here in step 3. So this is step 1, this is step 2, this is step 3. I copy the beginning of step 3 and the end of step 3. Limit as x approaches infinity from natural log y equals natural log 2. And then what do I need to do? I need to, in step 4, swap the operators. Remember, under certain conditions, and those conditions must be continuity. So natural log of the limit of our function when x approaches infinity equals natural log 2. So what could this number be? Look carefully. Natural log of a number equals natural log 2. What can this be?
2.
Exactly 2. Nothing else. No doubt. Only natural log 2 equals natural log 2. So I go back and finalize the limit. What do I write? I write 2. Would you have dreamed to see infinity raised to 0 being 2? Would you have dreamt? No. Okay, good. It's 2. Good. Anything else? So that's why they're called indeterminate. We have no clue what they lead to. And if you remember, there are 7 indeterminate cases. Okay, anything else that you would like to review?